This is the first time we've spoken about it, and this is mostly an introduction talk and to explain why we're doing it and what we're doing and so on and so forth. Do we need to read this or?
No.
Just. So let's start off by introducing the team that's involved. We've got Jared, who's put a lot of work into the HackRF project before. We've got Marshall, who's quite well known for doing strange things with N64 video games, building HDMI adapters for N64, things like that. Mike Kershaw, you may know him better as Dragon from Kismet. He's doing a lot of hardware design and other work with us. This is Mike Ossmann. It's me, and then we've got Benjamin, who is just sat up here actually. Just don't give us, come on.
Give us a wave.
Give us a wave. Okay, he's there. So he's another person you can ask about the project anytime over the next couple of days. If you're looking, the other guys aren't here, but the three of us are. So most of this project came from something that Josh Wright said, which is that security will not get better until tools for practical exploration of the attack surface are made available. And and we take this to heart. We take this to mean that, you know, we're not going to look at the security of a communications protocol. That's the kind of thing we're into, communications protocols. And we're not going to look at the security until you can look at it from the physical layer. Or, you know, we've done this for Bluetooth with the Ubertooth. The idea was to get in at the lowest level possible so that we can then explore up the stack. It's the same idea behind HackRF and things like that. So, you know what? How did we get to the state we are in with, say, Wi-Fi encryption? Right? We started off with open networks, and we had WEP if you wanted it secure. And Wi-Fi hardware from day one had arbitrary packet monitoring modes, and we were able to, as a community, use that to discover the flaws in web. And we got WPA, and then we were able to use the same process to discover the flaws in WPA, and now we have WPA2, and everything is perfect. And the same thing happened for Bluetooth to a certain extent, in that the analysis on the pin was a theoretical attack by Woolen Shaked. Always get that wrong, I'm sorry. And then we were able to show that that's actually practical with tools like BT Crack and with some of the GR Bluetooth stuff. We were able to look at that it is possible to brute force pins, and now we have secure simple pairing. And Mike Ryan is currently using Project Ubertooth to explore the pairing mechanisms at the physical layer in Bluetooth Low Energy, and he's already demonstrated last month that there are flaws there that need to be addressed, and so on and so forth. And this is great, and this is something that we could do really well with wireless, because you can build a sniffer or a monitor, and you can monitor these things out of the air. But we're quite curious about, well, why should wired protocols be any different? Right? Why have you got AES-grade encryption on your Wi-Fi connection and nothing on your Ethernet connection? And we think it's going back to what Josh Wright said, is because there are not practical tools to explore the security of some of these protocols, and certainly at the speeds that we'd like. So why the physical layer? As you can see from our incredibly complex diagram, we want to go in at as low as possible, at the lowest possible layer, because the lowest layer, the physical layer, encapsulates all of the higher layers. So if you can start to observe packets at the physical layer, you know that you can investigate the security of the link layer, of various other layers above that. Suddenly my mind's gone blank about the layers in the OSI model. But if you're looking at a higher layer, you can't look at the lower layers from that point. So we're trying to go in as low as possible, and that's what we've always done with other protocols, and that's what we want to do for these higher speed wired protocols. So,
sure. So there are certain target technologies that we are focused on in this project. In particular, we are building a device that can do monitoring of gigabit Ethernet, USB, not just USB 2.0, but USB 3.0, super speed, HDMI, and RS-232. RS-232 might sound like a little bit of an oddball here. Mostly we're targeting high-speed communications technologies that have previously been more difficult to monitor. But RS-232 is still around, and it has some characteristics that make it a useful test platform for us, that we can validate our platform works with the low-speed technology before we move on to some of the higher speeds. But ultimately, we're trying to make something that can attack or defend, be used to explore any wired communication technology. And these are just the first 4 that we're trying to target. There are existing monitors out there. For example, to monitor Ethernet, you could use my Throwing Star LAN tap. And it's just a simple, passive electrical connector that allows you to tap into Ethernet connections and monitor them. But it has some drawbacks. It only operates at 10 base T and 100 base TX. So it can't be used for gigabit Ethernet monitoring. There are a number of other passive LAN taps on the market or home-built circuits that accomplish the same thing. More commonly, people use a mirrored port on a switch to monitor gigabit Ethernet. And it has some drawbacks too. For one thing, a switch is typically visible to the target network. So it's not a particularly stealthy way to monitor an Ethernet connection. People also often use a software tap, like just generating a PCAP file on a host computer at one end of the connection, for example. And that definitely has a lot of uses, but it's at a higher layer of the protocol stack. And we want to be at the lowest possible layer. We want to be at the physical layer. We want to be undetectable, or at least as undetectable as possible. And we want to do this all in a portable, open source, low cost platform. USB. There aren't as many tools out there for monitoring USB, and they're really not very popular at this time in the information security community. There is a product line called Beagle from Total Phase, and these are some really nice boxes, but they're pretty expensive and closed source. The entry-level super speed USB monitor from Total Phase is like $3,000 or $4,000. It's not very affordable. There's also the USB, however you pronounce that, that is a lower cost commercial box that you can buy to monitor USB connections, but I think it only works at low speed and full speed. I don't think they support high-speed internet, and high-speed USB. They definitely don't support super-speed USB. One of the most exciting things that I've seen is the Open Vishla project, which is working on a monitoring device, an open source monitoring device for high-speed USB. And this would be really great if they would actually ship, but they haven't yet, and they've had my money for over 2 years. So I'm calling them vaporware for now, but I have high hopes. But even if they succeed in their goals, they won't be supporting super speed USB, and we think that down the road, that's going to become a very important capability. HDMI is a technology that hardly anybody does any monitoring of, but it's becoming more interesting from a security standpoint. Not only does HDMI carry video data, but it also carries low-speed serial communication, and it also, going forward, is going to be able to start carrying things like Ethernet over HDMI. So it might be useful to actually be able to interface with HDMI for security research. And there are a few interesting projects out there. There's NETV, made by Bunny Wang, which is a little FPGA platform that does HDMI man-in-the-middle stuff. That's pretty cool and very similar to what we want to do, except it doesn't really have any monitoring capability that we can tell out of the box. It doesn't have very much RAM. It doesn't have a buffer to store any data that it would pull from the wire, and it doesn't have a high-speed connection to a host computer that you could use to dump that data off. So it's good for certain things like injecting video into a connection maybe, but it's not a complete monitoring solution. And it only operates up to a certain pixel rate. HDMI runs at a very wide variety of speeds, of data rates of the video signal. And any TV operates just fast enough that it can do 1080i resolution. Well, 1080p is very common, and it's not supported by any TV. And so it would be nice to have something that supports 1080p and up. The Bus Pirate is a very low cost, very useful device that can be used, as Adam Laurie pointed out in his blog recently, for monitoring the control signals of HDMI. And these are the low-speed serial control lines. And this is pretty cool and definitely useful, but it's totally limited to just the low-speed control signals and not the video data, which is part of the package. The Video Ghost is the only kind of affordable HDMI monitoring device I've been able to find. And it only captures still images. Periodically, it grabs a still image and stores it. This is kind of cool, but it doesn't really meet the needs of a security researcher, I don't think. All of these existing monitoring solutions have certain drawbacks. Most of them are closed sourced. Most of them perform inadequately in some way. Most of them are expensive, not portable. And most of them operate at the link layer or higher. And as Dominic mentioned, we want to get to the lowest layer we possibly can because that gets us all the layers. A particular bottleneck that I want to point out, a particular flaw in the design of many different monitoring solutions for communication media is the bottleneck illustrated here. If you have a gigabit Ethernet tap and you put it on an Ethernet network, now that target network is full duplex, 1,000 megabit full duplex. So it's got 1,000 megabits going one way and 1,000 megabits going the other way, or up to 1,000 megabits going the other way. Well, if both directions are very active and close to their maximum capacity, the tap is trying to deliver potentially up to 2,000 megabits per second to the monitoring station. And in all of the lower cost, more portable solutions I've found, that connection from the tap to the monitoring station is a gigabit Ethernet line that can only carry 1,000 megabits in one direction. So there's a bottleneck. Something has to give here. What do they do? They have to either degrade the performance of the target network, or they have to drop some of the packets that are supposed to be delivered to the monitoring station. The best solution would be to add a higher speed or multiple connections from the tap to the monitoring station. And once you do that, it becomes less portable, right? Because you probably only have 1 gigabit Ethernet port on your laptop. So if you want a portable solution, it's only going to be able to connect on 1 gigabit Ethernet connection to your laptop. So this is one of the problems that we're trying to solve with this project. And it's one of the ways that we're trying to solve it is by using a USB 3.0 super speed connection to the host computer. USB 3.0 is becoming very popular. Most new laptops these days have it. So if you have USB 3.0 on your laptop, why not use that to deliver data, because it's the highest speed interface that's available to you commonly on a laptop that you might be carrying around in your bag anyway.
So with all this in mind, all these things, we decided we need to build a device. So we started writing down ideas, and the first thing that's really important to both of us and everyone involved in the project is open source. All our previous projects have been open source software, open source hardware. So we're pretty passionate about that. We need the performance to be able to monitor full duplex gigabit Ethernet connections. We also want to look at super speed USB. We want to look at all these things. We need enough performance to be able to get that data back to a host monitoring station. Portable would be nice. It's no use to us if it takes a rack to store this thing. Ideally, small enough to move around so that you're looking at a piece of technology, maybe on a client site or at work or at home or whatever, and it's easy to take this thing around. Now, we're not going to be able to build something that does all of this in one go, and it will probably be unwieldy and huge. I mean, just look at the amount of I/O on this board in front of me, and that doesn't do anywhere near the stuff we want to do. So we're going to build it modular. We're going to. The idea is to have something that I want to monitor USB today. Okay, I'll plug the USB front end on, and so on and so forth. And this means we can extend it in the future as well. And there's no use in us building terrible tools to use it with when everybody who wants to monitor these things knows Wireshark, right? So you want to be able to get your data into Wireshark. Like, you literally, I've got a communication protocol, I've got Wireshark, I just want to get it from one place to the other. And that's what we're going to try and do. So we named it Daisho. Daisho is a pair of swords worn by samurai, is that right?
Yes.
Yeah. For the modular design. I wasn't in IRC the day.
Good job.
Yeah, the day we decided I wasn't in IRC. But so the plan is to use standard PHY chips that are in your network card or your USB adapter already, and convert them from the physical protocol over the wire to whatever bus they speak internally, and then tap that data and pull that data back to the monitoring station. So as close to the physical layer as we possibly can. You don't really care about the varying voltage levels at the physical layer. What you just want to know is the physical bits. Because we need to be quite flexible and we need to do a lot of these things at high speed, we're going to put that through an FPGA. Back to the host as USB 3 super speed. As Mike said, it's common on laptops, it's common on desktops now. It's the fastest port to get data into your monitoring station. So it gives us the best hope for the future to continue being able to use this platform. And yeah, as I said before, a modular design so that if in a year's time there's a technology launch that everyone suddenly wants to be able to monitor, well, we can just build a new front end. We don't have to redesign the whole board. We don't have to change anything. We just get a couple of PHYs, put them on a front end board and plug it in. I make it sound simple, but it's not.
So this is the hardware architecture. It's two boards that work together. The main board is mostly what Dominic was just talking about. There's an FPGA with some RAM and a micro SD card for the FPGA bitstream. And a USB 3.0 connection that is intended to be connected in most use cases to a host computer that is the monitoring station. Connected to the main board is a module, a front-end module, and this is where we use an off-the-shelf PHY chip, physical layer transceiver, for the particular communications medium, and a connector for that medium. And so we have, in particular, something that's important to note is that these PHY chips, for most of the technologies we're looking at, normally you would have, let's say on a gigabit Ethernet card, you would have a PHY chip and a MAC chip that does the MAC layer. And we're just doing away with the MAC chip and connecting the PHY chip directly to an FPGA, so that we're getting to the lowest layer we possibly can and giving you the capability to create tools for monitoring or injection on this system. Notice that we have two PHYs and two connectors on each of our front-end modules. And the idea is to be able to plug in this platform in line into the middle of a connection. It's possible for at least some of these communication technologies that we could design our front ends to do passive monitoring, but our main goal here is to create tools that let you actually sit in the middle of a connection. And so the data might come in on one of those connectors through a PHY, over to the main board into the FPGA, and then back over to the other PHY and out the other connector. And this means that all the data on the target network is going through the FPGA. That gives us the ability to then duplicate that data, store it in the buffer on the RAM, send it over the USB 3.0 connection, do whatever we want with it. And it also opens the door to all sorts of interesting capabilities where we could inject onto the communication medium and operate as a man in the middle on the communication medium, which is something that there haven't been good tools to do on a wide variety of physical wired communication systems, in particular on high-speed wired communication media. So our goal for this project is really just to provide the hardware platform and the monitoring capability. But in the long term, we hope that people will be able to use this platform to perform things beyond monitoring. Is this mine? I don't know.
Whichever.
We have no idea whose slides are whose.
I can run with this one. Like I said earlier, open source is sort of important to us. We believe it's actually a pretty sensible philosophy for anyone to use in this industry. And so having said that, we will use as much open source, we'll produce as much open source software and hardware as possible with this project. All of our tools will be open source. The hardware designs are already on GitHub. The FPGA cores that we're writing are also going to be on GitHub, and they are already on GitHub. The only thing that is not open source are some of the FPGA tools, and we don't have any control over that. But where we've had to use closed source tools, they are at least freely available. So they're zero cost. And it would be nice if there were open source tools for FPGAs, but I think we're a little way off that.
The main board, the FPGA we're using on the main board is an Altera Cyclone 4 with about 30,000 logic elements, which is not one of the smallest FPGAs, not one of the largest FPGAs. It's kind of the FPGAs that are available with free-to-use tools, it is kind of moderate sized. And we have a USB 3.0 transceiver, just the PHY chip, on the main board, some DDR2 RAM, a small ARM microcontroller that's really just there primarily as a supervisor for the FPGA to load the bit stream and stuff like that, and a micro SD slot for storing the FPGA bit stream, and a front-end connector. The USB 3.0 PHY chip is a Texas Instruments TUSB 1310A. This is one of two super speed USB 3.0 chips that you can run out and buy right now. One is this Texas Instruments PHY, and the other is an ARM microcontroller with a built-in USB 3.0 device controller from Cypress. And the Cypress part is quite expensive. We could have used it here, but we said, hey, we could save some cost and use the PHY chip and write our own USB 3.0 device core to run on the FPGA to run this thing. And if we actually accomplish that, then hey, we have the world's first open source USB 3.0 device core that we just give to the world, which we think is worth doing. So we're doing that, and actually that's Marshall's job primarily. We just started this project in January, and he already has USB 2.0 device core working. And has tested successfully every single transfer type for USB 2.0, and he's starting on 3.0 now. So that part of the project is going well. You can, and actually, if you have any experience with these transceiver ICs for USB, the USB 2.0 interface that goes between a transceiver and a device controller is called ULPI, And with USB 3.0, it just adds a whole bunch of extra pins onto that, but it still retains ULPI for the USB 2.0 functions. So we now have a ULPI capable device controller. Even if we weren't to make any further progress, you could take what we have right now, take an FPGA, take an off-the-shelf ULPI that you can buy for $1, and stick them together and use our core to implement a USB 2.0 device.
I'll take this one.
Yeah.
So this is our development platform. It's up here in front of us at the moment. We ripped this photo off the manufacturer's website. This has a slightly larger Cyclone 4 chip on it, just to give us a little bit of wiggle room while we're doing our development. And so at the moment, we're building front-end boards for this while we're designing our own platform at the same time. It just enables all 6 of us to work on the project at the same time without having to wait for the hardware designs to be done and so on and so forth. It's got loads of I/O on it. We've actually also bought additional comms cards that come with it to play around with. So there's a USB, there's a ULPI.
Mm-hmm. There is a ULPI
on the comms card, and so we can use USB 2 on it and things like that, and so on and so forth. So at the moment, we're building these front-end modules. The first is everyone's favorite technology, RS-232. I have the board here. It just connects via a ribbon cable. As Mike said earlier, RS-232 was just an opportunity for us to experiment with a technology that we knew we weren't going to have performance problems with. We weren't going to have trouble understanding. It's fairly well known. And it was a technology we thought we could get devices for. And if anyone is following either of us on Twitter, you will know that we were hoping to demo talking to an old US Robotics serial modem. And the thing about US Robotics serial modems is most of them were built before everything came with an auto switching power supply. So we blew it in my hotel room last night when we plugged it into the 240 volts power. So we don't have a modem anymore, but we're still going to give you a little demo. So this has 4 ports on it. We can monitor 2 connections at a time. Today we're actually going to use one set of connections to monitor the other because I don't have my USB board with me to be able to backhaul the data over USB, and I didn't have time to write the code for that either. So there are 2 complete connections. So there are 2 connections for connecting to a PC and 2 connections for connecting to a device. DTE is data terminal equipment, and DCE is data communications equipment. And they use very similar parts for the PHY on both, and it's just to do with the direction that your number of pins. So one has 5 transmit pins, and the other has 5 receive pins, and so on and so forth. And in fact, you'll see on this diagram, if I wiggle the mouse a little bit, here they originally had rows of jumpers so that you can just do a connection straight through. But we're actually taking the data now, I've taken those jumpers off, and we're doing pretty much the same thing within the FPGA. It's incredibly simple code. It's pin 1 equals pin 2, all the way down the list. So it took me a long time to write that. This is the gigabit front end. There is only one of them, and it's got a fault, so it's still in Colorado.
I should have brought it anyway.
Yeah, we didn't bring it with us.
Hey, there's a photo.
Yeah, so this is what it looks like. If you can see the fault, then you can have it. It's got 2 micro PHYs on there, and then they speak GMII, which is the protocol that they would normally speak to the MAC layer with. We're going to use that across this high-speed mezzanine connector to talk to the FPGA, and then we're just going to tap that level. So that's somewhere between level 1 and 2 on the. It's not quite physical layer tapping, but it's as close as, right? Mm-hmm. We'll take that back to the host because there's no point in us doing anything with that on the FPGA. We may as well get as much data as possible back to the host. And the nice thing about tapping at that level, again with this, is that when you come to do man in the middle, you can do things like flip bits in the middle of it and see what happens, which you can't do if you're tapping at a higher level. So, The next module we're designing at the moment is the HDMI front end. Now, there aren't readily available 5 parts that do what we want for the HDMI, so we're going to use generic serialization, deserialization chips. And the idea is we will deserialize the connection from, there are multiple pairs of pins within an HDMI connection, pass them all through the SERDES into the FPGA, and then back out through another one and on the way. At 340 megahertz, we should be able to support all of the existing resolutions in the 1.4 spec, so that's 1080p, that's 1080p with the dual images for 3D, that sort of stuff, and various other protocols. The only feature we won't be able to support in HDMI 1.4 at the moment is Ethernet. Now, we are interested in supporting it, but the spec has not been released, so we have no idea how it operates because we can't get hold of the spec. If the spec is released at some point, or if a copy were to just end up on my doorstep, then I don't see why we wouldn't be able to support it. If we can support the high-rate video stuff, it's surely very similar. Like there can't be anything technologically.
Yeah, and
outside.
Eventually we might, if they don't release a spec, we might have to just reverse engineer off-the-shelf products. But as far as I know, there's only one product on the market that supports Ethernet over HDMI, and it's like $10,000, and there's nothing for it to talk to. So it's probably not worth trying to do that yet.
Right. Right. I mean, we're really trying to be on the cutting edge of that, but we're just slightly behind. So, okay, USB 3. Now, the conversation surrounding when designing this board was over email, and I sent Mike an email saying, "Hey, we should tap using USB as the data backhaul." And he went, "Yeah, let's do gigabit." And I was like, "Oh, okay, we'll do gigabit, and we'll have to use USB 3 as the backhaul." And he goes, "Oh, we should tap USB 2 at the same time then." "Oh, well, why don't we tap USB 3? And it just kind of escalated and got a little out of hand, and that's how we end up with HDMI and USB 3 modules. And this is going to be based on exactly the same transceiver chip that we're going to have on the main board. It's the TI part, and those paying attention in the audience will have spotted that this comes with the same problem that we were describing about tapping connections earlier. How can you tap a 5 gigabits full duplex signal if you've only got 5 gigabits back to the host? And we completely understand that that's a problem, but we don't think it's going to be a problem in reality, because I have yet to see any USB 3 devices that that max out the 5 gigabit connection anyway. The only ones that are likely to do it in both directions are potentially hard drives, and I'm not sure any of those support reading and writing at full speed at 5 gigabits in both directions at the same time. There might be.
Yeah, because they're going to be more limited by the actual hard disk itself.
Yeah, there might be some solid state stuff
connection
in the future, but
Right.
but again, most of those are using things like SATA inside and stuff.
Right.
So we don't think that's going to be a huge issue. We also think if anyone does that, it's going to be bursty. So we'll probably be able to buffer it in the RAM on the motherboard at first. I'm aware most of this sounds like an excuse, but and then if that starts being a problem, 10 gigabit USB 3 has just been announced. So maybe in the future we'll look at ways to support that or something like that. But for now, we think we'll be able to successfully tap most connections. I should also we aren't building a USB 3 dev board for this, because it turns out to have 2 USB 3 PHYs requires more pins than the mezzanine connector on this dev board can support. So we tried to build one, but there just weren't enough pairs of pins that we need to get the pipe protocol across the connector. So we're just going to save that for the final front end, the final board. But we're hoping that time-wise, there's plenty for us to be doing with the other protocols. So, check out that slide that actually says demonstration.
It's Dominic's demonstration.
Demonstration. Yeah, I can't believe we haven't come up with this before. Maybe because it's a terrible gag. So, just to explain what's going on while Mike's setting this stuff up, we have 3 USB to serial connectors. They just look like this. They're a USB to RS-232 adapter. We have 3 of them plugged in. 2 are linked back to back through in fact, if I unplug the tapping port, go for it.
Why are you doing this?
I was going to say, if you just go for it with the first 2. And you should be able to see that we're passing data backwards and forwards between.
Oh,
I'm
right.
just gonna,
Right.
So,
That's not working.
yeah.
Oh, yes, it is.
Yeah.
Right. My focus was in the upper window, and my typing came out of the bottom.
Yeah. The thing to remember
So-
is there's no local echo.
Yeah.
So unfortunately,
Local echo. So I'm typing in one, and the text is appearing in the other window.
and it's
right?
just going out and through it. Yeah, that's right. We're tapping a serial connection. We're passing through a serial connection. Now, if I plug in the tapping port on this third one,
This is just another USB serial connector.
just another, yeah.
And so now I should be able to type and see that it appears in both the destination port and also our tapping port.
Yeah. Really? Yeah.
Really?
Thank you. I think that might be a world first for that technology. Getting a round of applause.
Yeah.
Now, we're actually here because we're using data backhaul over RS-232. We're only using one connection. We would have two connections if we hadn't destroyed the modem. But we can only monitor, we can only monitor in one direction because we suffer from the same problem that RS-232 is a full duplex communication technology. And so therefore we can't monitor both connections at the same time, both directions at the same time with a single tapping port. I mean, we can because the data rate's so low, but we didn't have time to write the code between destroying the power supply last night and this morning. So
Right. And ultimately, this is actually kind of a weird use case that that wasn't even our goal in the first place. We threw some extra ports on the RS-232 board just because they were cheap and we had room. Ultimately, we really only need 2 ports on that board, not 4, and we'll be passing this data back over that back-end USB connection, not over to yet another RS-232 port.
Right. That's the slides. So the software that we're going to build for this, there'll be various cores written for the FPGA, but the main one is the USB 3 that we've already talked about. And then most other things will attempt to get as much data back to the host as possible. There's no point in us implementing chip MAC layer and things like that within the chip because we want that data back on the host. So we will have libdaisho that's just going to handle the USB transfers, pull the data back, and then in general, almost everything we're going to attempt to get into Wireshark. I think that works for most of the technologies we're looking at. Use Wireshark to analyze the data. You can write plugins for Wireshark to process the various things at the physical layer that may not currently be supported by Wireshark. And we'll be doing that for the technologies we're looking at. We're also working with the Wireshark team to extend Wireshark to enable it to sniff using different hardware. So the idea is that we're changing the capabilities of the way Wireshark accesses hardware to dump data so that it will support Daisho and so that it will support, we're actually doing it for Ubertooth as well. So the Wireshark guys are working with us on that.
And in the future, we hope to support more target technologies. In particular, we're very interested in high-speed communication media because those are the things that we haven't had good tools to work with in the past. DisplayPort is interesting to us, DVI, SATA. Dominic had this idea the other day that we should be able to just make a phone tap. And not just any phone tap, but one that can capture both audio and things like DSL. That would be way cool. Really any communication technology that we can find a way to interface with, we think would be worth making a front-end module for in the long run. We're also hoping to see some third-party modules. It's really easy to design a board that has a connector to connect to a Daisho mainboard. And so that gives you an FPGA and a USB 3.0 super speed connection to a host computer. What can you do with USB 3.0 and an FPGA? We think this is a really cool thing. There are some other open source hardware FPGA platforms out there, but none of them have USB 3.0. And if you're going to have a device like an FPGA that can handle very high data rates, why not have the highest speed connection in and out of that thing that you possibly can?
So we should say, like, it doesn't have to be a tap or anything like that. It could be
Right.
any kind of I/O. So you want to build some kind of camera or something that needs huge amounts of data back to the host. We've got a lot of pins, and we've got a USB 3 connection, and you have to write a very small amount of Verilog to get your data into your host system. So we think that's pretty straightforward, and that's a big deal too.
Mm-hmm. And maybe people will make new Daisho mainboards too. I don't know. But the design's out there. It's all open source hardware and open source software, so you can do whatever you want with it. Ultimately, we would like to pursue maybe some wideband software-defined radio front ends for this platform. It's a pretty well-suited platform for that. This picture has nothing really to do with Daisho. This is my HackRF project that some of you guys know about. I'm trying to build, with the HackRF project, I'm trying to build a very general purpose, low-cost software-defined radio platform. It's USB 2.0. Not USB 3.0. And for HackRF, I'm trying to get the most out of USB 2.0 that I can. But down the road, building upon the Daisho platform, we should be able to build front-end modules that get the most out of USB 3.0, which could be really, really cool. Like one of the things, actually Dominic and I met because we were both trying to develop ways to monitor Bluetooth. And one of the first things we worked on was how can we use software-defined radio to monitor all 79 Bluetooth channels simultaneously? And we came up with kind of a kludgy way to do that, but now this may be finally the opportunity where we can do it the right way and just suck in the entire 2.4 gigahertz ISM band from an antenna through a USB 3.0 connection into a host computer and monitor all of it. We think that would be really cool. So a couple of thanks. This project is supported by the DARPA Cyber Fast Track program. And hopefully some of you guys have heard of the CFT program. It's a very interesting program from DARPA, the Defense Advanced Research Project Agency in the United States, to fund work within the information security community. And I want to point out that I've had multiple projects funded by CFT. It's really been a pleasure for me to be able to participate in that program, get projects of mine that I've wanted to do for a long time, but I haven't had the resources to be able to pursue them. CFT has enabled me to do that. And there are a couple of weeks left. April 1st is the deadline to get proposals in. If you have an idea, if you have some project you've wanted to do that's a information security related research project that you could use some funding for, then get in a proposal. Something a lot of people don't know about CFT is that you do not have to be a United States citizen or resident to submit a proposal. So, first time ever. This is one of the really cool things about this program. So, if you have an idea, if this maybe piques your interest and you need any help or advice with submitting a proposal, come talk to me this week because I've been through it and I can help you out. Also, thanks to Bit Systems for their help with the Cyber Fast Track program. They've been really great to work with. The information about Daisho, ultimately, I hope to make these things and sell them on greyskygadgets.com. But right now, you won't find any information about Daisho there because this project is in its infancy. Mostly the information that we have available is our GitHub repository. Everything we're doing is on GitHub, and mostly the developers talk about it in the Daisho channel on freenode.net. So GitHub and IRC, we'd love to see more people come and hang out and ask questions. Dominic and I will be here the rest of the con, and we hope that if any of you have any interest in this project, we'd sure love to talk to you.
Yeah, we'd love to hear.
I'm going to point out Benjamin again. Yay, Benjamin. He's one of our developers who was kind enough to make the trip from France so that we could actually meet him in person for the first time. The way he got involved in the project was He just showed up in the HackRF IRC channel one day last year and started writing code. And I'm like, wow, this is great. How would you like to help with this other project? So thanks to Troopers, and I think we have maybe a few minutes for some questions, if there are any. If there are any.
Thanks. You've been talking about DisplayPort. Actually, what about PCI Express flowing on Thunderbolt?
We had a discussion about Thunderbolt last night.
We did. Thunderbolt is interesting. One problem with Thunderbolt is that it has, you can't buy a chip for it. It's only implemented by Intel, and I don't think there's any hope of buying small quantities for research and development. If we're not going to buy 1 million of them, we're probably not going to get any. The only way, and also it's about twice as fast as USB 3.0. And the only way we could use, like the technique we're using to interface with HDMI is to use a generic SerDes chip, which is a little different than most people do. But there are no generic SerDes ICs that I know of that go fast enough to implement Thunderbolt. The only generic SerDes implementations that I know of that go that fast or faster are on high-end FPGAs, which require development tools that cost money, which we're trying to avoid. So ultimately, we may, and even if we did support it, we'd have this big bottleneck where we're trying to run data over USB 3 that was carried on Thunderbolt. So there are a lot of drawbacks or roadblocks to implementing Thunderbolt. And
we've also got a big list of technologies we're interested in, and it is on the list. But given the amount of time it's going to take to implement all of those, the landscape of sort of various communication technologies connecting back to hosts and the ports on various hosts is probably going to change over time. So if Thunderbolt suddenly appears on the next generation of laptops and is there for the next few years, then maybe down the road there'd be a future Daisho which uses Thunderbolt as its data backhaul and maybe supports it, but we don't have access yet to the technology to support it.
And as Dominic mentioned earlier, the next generation of USB has already been announced, which is 10 gigabit. It's basically double super speed. Yeah. It doesn't exist yet, but assuming that does come out in a couple of years, we may develop, like the next generation Daisho platform based on that, and maybe at that time it would be more practical to implement Thunderbolt.
Also, if we're lucky, USB 3 at 10 gigabits will kill Thunderbolt, and then we won't have to worry about the problem. That'd be nice.
Any other questions? All right. Thank you, everybody.
Thank you very much.
One more?
One additional question.
Sorry.
Actually, it was a two-side question. Since Thunderbolt embeds PCI Express, PCI Express is certainly more doable, and you have only one channel instead of something like 8 half duplex. So what about this? I think this part is quite interesting actually in terms of hybrid devices that enable on top of that attacks through the DMA.
Yes, and this is definitely an area of interest for us. Sorry, I forgot you mentioned PCI Express in your original question. I think that there is some potential there, and Thunderbolt in particular has its problems, but PCI Express is within the realm of possibility of us supporting. We don't have plans for a front-end module today, but it is an area that we're interested in. We would like to work on front-end modules for, and we're very interested in being able to support not just inline monitoring, but like you mentioned, DMA attacks over PCI Express, that kind of stuff, we think is really important that we hope our project will enable in the long term.
Yeah. And there's nothing to stop someone else, an interested party, working on a front end, even if we don't have the capacity to do so at the moment. I mean, obviously you might want to wait until there are Mainboards available, but certainly it's all open, and we'd be more than willing to help out anyone who was interested in looking at other technologies.
Yeah,
So,
definitely.
definitely, if you're keen.
All right.
All right.
Okay, so Mike, Dominic, thank you very much.
Thank you.